Tonight, we're going to explore one of the biggest mysteries in modern space exploration: the Moon. Humanity walked on its surface over 50 years ago. 12 astronauts left their footprints in the lunar dust between 1969 and 1972. We had the technology, we had the capability, we proved it was possible, and then we stopped. We never went back. NASA just launched Artemis II in the beginning of April 2026, sending astronauts around the Moon for the first time in over half a century. But here's the thing: they didn't land. An actual lunar landing won't happen until at least 2028. We haven't actually landed on the Moon in over 50 years. An entire generation has been born, grown up, and grown old without witnessing a lunar landing. By the end of tonight, you're going to understand why we stopped, what it actually took to get there in the first place, and why going back is far more complicated than most people realize. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what actually happened. The Apollo program. Most people know the basic story. America and the Soviet Union were locked in the Cold War. The space race was part of that conflict, a way to demonstrate technological superiority without firing missiles at each other. The Soviets struck first. October 4th, 1957. Sputnik 1, the first artificial satellite, launched into orbit. A small metal sphere weighing about 184 pounds or 83 kilograms, beeping its radio signal as it circled Earth every 96 minutes. That beep terrified Americans. If the Soviets could put a satellite in orbit, they could put a nuclear warhead in orbit. They could strike anywhere on Earth with almost no warning. The technological gap seemed enormous. Then came Yuri Gagarin, April 12, 1961. The first human in space. The Soviets were winning, and it wasn't close. America felt the sting of defeat. President Kennedy needed a goal that would rally the nation, something bold enough to capture the world's imagination and ambitious enough that the Soviets couldn't easily match it. On May 25, 1961, Kennedy stood before Congress and made a promise. America would land a man on the Moon and return him safely to Earth before the end of the decade. Not just reach orbit, not just send a probe, land a human being on another world and bring them home. At the time, America had achieved exactly 15 minutes of human spaceflight experience. Alan Shepard's suborbital flight had happened just 3 weeks earlier, 15 minutes. And Kennedy was promising to send astronauts to the Moon, 250,000 miles away, within 9 years. It was absurd. It was impossible. It was brilliant. Because going to the Moon required solving thousands of problems that had never been solved before. It required inventing new technologies, new materials, new techniques. It required an effort so massive that the Soviets couldn't simply copy what they'd already done. It leveled the playing field and forced both nations to start from almost zero. NASA had been created in 1958, just 3 years earlier. The agency barely existed. The technology needed for a moon landing didn't exist. Nobody knew how to do it. Nobody had ever built a spacecraft capable of leaving Earth orbit. Nobody had ever performed a spacewalk or docked 2 spacecraft together or operated in the vacuum of space for more than a few hours. All of that had to be invented from scratch. The Apollo program cost roughly $25 billion in 1960 dollars. Adjusted for inflation, That's over $250 billion today. At its peak in 1966, the program employed over 400,000 people and consumed roughly 4% of the entire federal budget. 4%. Imagine the US government today dedicating 4% of its budget to a single scientific program. The political will required for that kind of commitment is almost unimaginable now. But in the 1960s, it happened. Why? Because landing on the moon wasn't really about science. It was about demonstrating that American technology could achieve something the Soviets could not. It was about winning the Cold War without firing a shot. The moon was the battlefield, and the Apollo program was the weapon. They achieved it. Neil Armstrong stepped onto the lunar surface on July 20th, 1969. 6 missions followed. 12 humans walked on another world. They collected 382 kilograms of moon rocks, or 842 pounds. They conducted experiments, took photographs, drove rovers across the surface. They proved it was possible. And then, after Apollo 17 in December 1972, it ended. No more moon landings. Over 50 years and counting. So why did we stop? The answer is complicated, but it comes down to 3 main factors: cost, politics, and purpose. The Apollo program was staggeringly expensive. $25 billion in 1960 dollars. Over $250 billion in today's money. That's more than the Manhattan Project, more than the Panama Canal, more than any peacetime project in American history up to that point. At its peak, the Apollo program consumed roughly 4.4% of the entire federal budget. 4.4%. In 2026 dollars, that would be equivalent to spending over $200 billion per year, just on space exploration, just on getting to the moon. For comparison, NASA's entire budget in 2026 is about $25 billion annually, less than half of 1% of the federal budget, a tiny fraction of what Apollo consumed at its peak. The scale of investment required for Apollo was extraordinary. It employed over 400,000 people directly. Millions more worked in supporting industries. Factories manufacturing rocket components. Companies developing new materials and technologies. Universities conducting research. Entire towns grew up around NASA facilities. Houston, Texas, became synonymous with space exploration because of the Manned Spacecraft Center. Huntsville, Alabama built its economy around rocket development. Cape Canaveral, Florida, became the gateway to space. The economic impact was enormous. But it was all happening during the Vietnam War. By the late 1960s, public support for the war was collapsing. The country was deeply divided. Protests were erupting on college campuses. Cities were burning in race riots. The assassinations of Martin Luther King Jr. and Robert Kennedy in 1968 shocked the nation. The government was spending billions on war and billions more on space, while poverty and inequality persisted at home. Critics asked the obvious question: why are we spending money to put men on the moon when we have problems here on Earth? The criticism was fair. America had serious domestic problems. Poverty, racism, inequality, urban decay. These problems weren't being solved. And meanwhile, billions were being spent on space. Once America proved it could land on the moon, the primary goal was achieved. The political purpose was fulfilled. We beat the Soviets. We demonstrated technological superiority. Mission accomplished. Continuing the program required justifying the cost every single year. And every year, that became harder. NASA's budget peaked in 1966 at roughly 4.4% of the federal budget. By 1970, it had dropped to less than 2%. By 1975, less than 1%. The money wasn't there anymore. Congress wasn't willing to keep funding moon missions when the immediate political benefit had already been realized. The budget cuts forced NASA to make hard choices. Cancel Apollo missions 18, 19, and 20. Shut down the Saturn V production line. Lay off thousands of workers. Close facilities. The infrastructure that made Apollo possible was dismantled piece by piece. Kennedy promised a moon landing before the end of the decade. America achieved that in July 1969. Mission accomplished. The goal that Kennedy set had been reached. And tragically, Kennedy didn't live to see it. But his vision had been realized. His challenge had been met. After that, continuing the program was harder to sell. The urgency was gone. The deadline had passed. The Soviets never landed on the moon. Their own lunar program, the N-1 rocket, failed in every test launch. 4 attempts between 1969 and 1972. 4 catastrophic failures. The first test in February 1969 ended when a fire broke out in one of the 31st stage engines. The rocket crashed less than a minute after liftoff. The second test, in July 1969, was even worse. A loose bolt was sucked into one of the engine's fuel pumps. The engine exploded. The explosion triggered a cascade failure across all 30 engines. The rocket fell back onto the launch pad and exploded. The blast was one of the largest non-nuclear explosions in history. It destroyed the launch pad and damaged facilities for miles around. The third test in June 1971 lasted longer, reaching an altitude of about 6 miles before a roll oscillation tore the rocket apart. The fourth and final test in November 1972 also ended in failure. The rocket was destroyed by a malfunction in the guidance system. After that, the Soviet Union gave up. They quietly cancelled the N-1 program. They never publicly admitted they were trying to reach the moon. Even today, there's debate about how seriously they pursued it. But the evidence suggests they tried hard and failed. So America won the space race by default. And once the race was over, the motivation disappeared. There was no competition, driving continued investment. The Soviets weren't going to the moon, so America didn't need to keep going either. The political landscape had changed fundamentally. The Cold War was still happening, but the space race component had ended. There was no political reward for spending billions more on moon landings. Public interest had already started to wane. The Apollo 11 landing was a global event. 600 million people watched it live. It was historic, unprecedented, transformative. Apollo 12, just 4 months later, received far less media coverage. The launch was hit by lightning twice. Both strikes happened within seconds of liftoff. The spacecraft's electrical systems temporarily failed. Alarms blared. The mission could have been aborted. But the astronauts and mission control troubleshot the problem in real time, reset the systems, and the mission continued. It was dramatic. It showed the skill and bravery of everyone involved. But the television networks barely covered it. The public didn't care as much. We'd been to the moon already. A second landing was just repetition. By Apollo 13, which suffered a life-threatening explosion en route to the moon, The networks weren't even planning to broadcast the mission live until the crisis happened. The explosion occurred about 56 hours into the flight. An oxygen tank in the service module ruptured. The blast damaged systems throughout the spacecraft. The crew heard a loud bang. Alarms started sounding. They saw the pressure in one oxygen tank dropping to zero. Then, the second tank started losing pressure. Within hours, the service module would be dead. No power, no oxygen, no water. Mission Control worked frantically to find a solution. The only option was to use the Lunar module as a lifeboat. Power down the command module to conserve its batteries for re-entry. Move into the LM. Use its resources to survive the trip back to Earth. It shouldn't have worked. The LM was designed for 2 people for 2 days. There were 3 astronauts, and they needed to survive for 4 days. They had to ration everything. Power consumption was cut to the bare minimum. The cabin temperature dropped to near freezing. Water was rationed to 6 ounces per person per day, barely enough to prevent dehydration. Carbon dioxide levels rose because the LM's scrubbers couldn't handle 3 people. Engineers on the ground improvised a solution using materials the crew had available: duct tape, plastic bags, and cardboard from the command module. The crew built a makeshift adapter that connected the command module's square CO2 scrubbers to the lunar module's round receptacles. It worked. It shouldn't have, but it did. Suddenly, the networks were interested again. Apollo 13 became the most watched space mission since Apollo 11, not because of exploration or science, but because it was a disaster, a crisis, a human drama playing out in real time. People tuned in to see if the astronauts would live or die. Fortunately, they lived. The mission was a successful failure. The crew made it home safely. But it highlighted something troubling. The public wasn't interested in routine moon missions. They were only interested when something went wrong, when there was drama, when lives were at risk. That's not a sustainable basis for a space program. Nixon became president in January 1969, 6 months before the Apollo 11 landing. He inherited the Apollo program, but wasn't particularly interested in space exploration. He saw NASA's budget as something that could be cut to fund other priorities. Nixon was dealing with the Vietnam War, which was consuming enormous resources and political capital. He was dealing with economic challenges, including rising inflation. He was dealing with social unrest and the civil rights movement. Space exploration was not high on his list of priorities. He attended the Apollo 11 launch. He spoke to the astronauts on the moon via a phone call from the Oval Office. He was there for the splashdown, greeting the crew aboard the recovery ship. He understood the public relations value, but he didn't see space as strategically important anymore. The political landscape had shifted. Nixon was pursuing détente with the Soviet Union, a relaxation of tensions. He visited Moscow in 1972, the first American president to do so. He signed arms control agreements. Cooperation was the new theme, not competition. And that meant the space race, which had been fundamentally about competition, no longer served a clear political purpose. The Apollo program was never really about science. The science was a bonus, a side benefit. The real goal was political. Demonstrate American technological superiority. Once that was achieved, the program's justification evaporated. Scientists argued that the moon had immense research value, and they were right. The rock samples brought back from the moon revolutionized our understanding of lunar geology, of the solar system's formation, of the history of impacts and volcanism. The experiments left on the Moon, seismometers and reflectors and other instruments, provided data for years. But those benefits, real as they were, weren't enough to justify the cost. Not when the political motivation was gone. Not when the public had moved on. Not when there were other priorities competing for funding. To truly grasp what was lost, you need to see what we actually built. The scale of achievement, the risks taken, the infrastructure created and then dismantled. The engineering challenges were staggering. Start with the rocket, the Saturn V. Still the most powerful rocket ever flown to this day. It stood 363 feet tall, or 111 meters. That's taller than the Statue of Liberty from base to torch. Taller than a 36-story building. When you stood at the base and looked up, you couldn't see the top without craning your neck back uncomfortably far. It weighed 6.2 million pounds fully fueled, or 2.8 million kilograms. Most of that weight was propellant. Liquid oxygen and kerosene in the first stage. Liquid oxygen and liquid hydrogen in the upper stages. The rocket burned through fuel at an astonishing rate. The first stage consumed 15 tons of propellant every single second. 15 tons every second. For 2.5 minutes. That's the equivalent of draining an average swimming pool every 10 seconds. The first stage alone, called the S1C, had 5 F1 engines. Each F1 engine produced 1.5 million pounds of thrust, or 6.7 million newtons. Together, the 5 engines generated 7.5 million pounds of thrust, enough to lift the entire vehicle off the launch pad and accelerate it to over 6,000 miles per hour, or 9,650 kilometers per hour, before the first stage separated. The F1 engines remain the most powerful single-chamber liquid-fueled rocket engines ever built. Each one stood 19 feet tall and weighed over 18,000 pounds. The turbopumps that fed fuel into the combustion chamber spun at 5,000 revolutions per minute, delivering 42,000 gallons of propellant per minute. That's enough to drain an average backyard swimming pool in under 20 seconds. The engineering required to make these engines work was extraordinary. The combustion chamber operated at temperatures exceeding 6,000 degrees Fahrenheit, or 3,300 degrees Celsius. Hot enough to melt steel instantly. The chamber walls had to be actively cooled by circulating fuel through channels in the metal, carrying heat away before it could cause damage. If the cooling system failed for even a fraction of a second, the engine would destroy itself. And these engines had to work perfectly, every time, because there was no backup. If even one of the 5 engines failed during launch, the entire mission would be aborted. The rocket would either crash or be destroyed by range safety officers to prevent it from falling on populated areas. The sound was incredible. People standing 3 miles away felt the vibrations in their chests. The roar was audible for miles. Cameras shook on their mounts, even though they were bolted to concrete pads. The ground trembled. Windows rattled in buildings miles from the launch site. The sound pressure level at close range was over 200 decibels, loud enough to be lethal if you stood too close without protection. The acoustic energy was so intense that NASA had to build a water suppression system that dumped hundreds of thousands of gallons of water onto the launch pad during ignition. Not to cool anything, but to absorb the sound energy and prevent it from reflecting back up and damaging the rocket. Every pound mattered. Engineers spent years figuring out how to shave weight from every component. Thinner metal, lighter instruments, smaller fuel reserves. The margins were razor thin. The skin of the fuel tanks was in places thinner than a dime. If you pushed on it hard enough, you could dent it with your hand. This seems absurd for something that had to contain millions of pounds of fuel under pressure. But the tanks were kept rigid by the pressure of the fuel itself. Empty. The tanks would collapse under their own weight. Fully fueled, they were incredibly strong. It was a brilliant engineering solution, but it meant the rockets were fragile. They had to be handled carefully during assembly. A single mistake, a dropped tool, a careless worker bumping into the structure could cause damage that would doom the mission. The tolerances were measured in fractions of an inch. Parts manufactured by different contractors across the country had to fit together precisely. There was no room for error. The 3 stages of the Saturn V each had specific jobs. The first stage, the S1C, lifted the rocket from the ground to an altitude of about 42 miles, or 68 kilometers. It burned for about 2.5 minutes, consuming almost 5 million pounds of propellant. Then it separated and fell into the Atlantic Ocean, never to be recovered, never to be reused. Just gone. The second stage, the S2, took over. It had 5J, 2 engines burning liquid hydrogen and liquid oxygen. Together they produced about 1 million pounds of thrust, far less than the first stage, but enough to continue accelerating the now much lighter rocket. The second stage burned for about 6 minutes, pushing the vehicle into a parking orbit around Earth. Then it too separated and fell away, discarded like the first stage. More millions of dollars of hardware thrown into the ocean. The third stage, the S4B, had a single J2 engine. This stage was special because it could restart. After reaching orbit, the crew would spend a few hours checking systems, making sure everything was working correctly. Then Mission Control would give the command for trans-lunar injection. The S4B engine would reignite, burning for about 6 minutes, accelerating the spacecraft to escape velocity. This burn was critical. If the engine failed to restart, the mission couldn't continue. The astronauts would be stuck in Earth orbit. But the J2 engine was designed to restart in the zero-gravity environment of space. Fuel had to be settled in the tanks using small thrusters before ignition. The whole system was complex and had to work flawlessly. After the trans-lunar injection burn, the S4B separated from the command and service module. The astronauts then performed a maneuver called transposition and docking. They turned the spacecraft around, docked with the lunar module, which was stored in the top of the S4B stage, and pulled it free. Then the S4B was sent on a trajectory that would either crash it into the moon, creating a seismic signal that scientific instruments on the surface could detect, or send it into orbit around the sun. Every piece of the rocket was used and then discarded. Nothing was brought back except the tiny command module, and after one flight, it was gone. The entire Saturn V rocket, everything except the tiny command module, was thrown away. Millions of pounds of hardware, billions of dollars of engineering, used once and discarded. Each launch required building an entire rocket from scratch. Manufacturing the F1 engines alone took months. Skilled workers had to hand-weld thousands of tubes for the cooling channels. The turbopumps had to be machined to incredible precision. Every component had to be tested individually and then tested again as part of the complete engine. Building a complete Saturn V took years and cost hundreds of millions of dollars. And after one flight, it was gone. This is one of the reasons the Apollo program was unsustainable. It was phenomenally expensive. Every launch required building an entire Saturn V from scratch. Every mission threw away hardware that cost hundreds of millions of dollars. It worked. It achieved the goal, but it couldn't be maintained indefinitely. The Apollo Command Module, the cone-shaped capsule that housed the astronauts, was tiny. About 12 feet tall and 13 feet in diameter at the base, or 3.7 meters by 4 meters. 3 astronauts lived in that space for 8 days. They ate, slept, performed experiments, navigated, and controlled the spacecraft, all crammed into a volume smaller than a walk-in closet. The interior was packed with equipment. Control panels covered every surface. Switches, dials, instruments, displays. Over 600 controls and displays in total. The astronauts had to memorize what each one did. During flight, they had checklists hundreds of pages long, telling them which switches to flip and when. One wrong switch at the wrong time could doom the mission. No bathroom. They used bags and tubes. The process was undignified and uncomfortable. No shower. They wiped themselves with damp cloths. By the end of a mission, the cabin smelled terrible. A combination of sweat, body odor, and the off-gassing from equipment. No privacy. They were together every moment for over a week. 3 people in a space the size of a car interior. They couldn't get away from each other. If personalities clashed, there was no escape. NASA tried to select crews who would work well together, but the psychological strain was immense. Some crews got along well. Others had tensions that showed in the mission transcripts. Sleep was difficult. The astronauts slept in sleeping bags attached to the walls or strapped into the seats. There was no day or night in space. The sun rose and set every 90 minutes while in Earth orbit. They had to follow an artificial schedule, forcing themselves to sleep when their bodies didn't want to. The constant noise didn't help. Fans humming, pumps circulating coolant, radio chatter, equipment beeping and clicking. It was never silent. Food was another challenge. Everything had to be dehydrated or freeze-dried to save weight. Meals came in packages that the astronauts had to reconstitute with water. The food was nutritious, but not particularly appetizing. Some astronauts lost weight during missions because they simply didn't want to eat. The menu tried to offer variety: beef stew, chicken, shrimp cocktail, fruit cocktails, cookies, but it all had a similar texture and bland taste. The most popular item was the shrimp cocktail. Astronauts often requested extra servings. Something about the tangy sauce made it more palatable than the other options. Drinking was done through a straw from plastic bags. Even this simple act required care in zero gravity. If you squeezed too hard, droplets would escape and float around the cabin. Water globules drifting through the air could get into equipment and cause short circuits. So the astronauts learned to drink carefully, controlling the flow. And all of this happened while they were traveling through the vacuum of space, hundreds of thousands of miles from Earth, with no possibility of rescue if something went wrong. The psychological pressure was enormous. When the astronauts returned from the Moon, they hit Earth's atmosphere at roughly 25,000 miles per hour. At that speed, air friction generates temperatures exceeding 5,000 degrees Fahrenheit, or 2,760 degrees Celsius. Hot enough to vaporize steel. Hot enough to turn the air itself into plasma. The heat shield on the bottom of the command module was designed to ablate, to slowly burn away in a controlled manner, carrying heat away from the capsule. During re-entry, the outer layers would char and vaporize, creating a boundary layer of gas between the capsule and the superheated air. This process carried away most of the heat, but the astronauts inside still felt it. The cabin temperature rose. They sweated in their pressure suits. Outside the windows, they could see flames. The spacecraft was surrounded by a sheath of fire. Radio communications were cut off for several minutes because the plasma blocked radio signals. This was called the communications blackout. During this time, Mission Control couldn't talk to the crew. They couldn't send commands. They couldn't receive telemetry. If something went wrong during the blackout, there was nothing anyone could do. The crew was on their own. And if the heat shield failed, the astronauts would burn up. There would be no warning. One moment, they'd be experiencing normal re-entry heating. The next moment, the shield would fail, and superheated plasma would flood into the cabin. Death would be instantaneous. Every Apollo crew faced this moment. Every re-entry. The moment when you're surrounded by fire, falling through the atmosphere at 25,000 miles per hour, with nothing between you and incineration except a few inches of resin that's slowly burning away. If the capsule entered at the wrong angle, too steep, and they'd decelerate too quickly, experiencing crushing G-forces that would end them. Too shallow, and they'd skip off the atmosphere like a stone on water, shooting back into space with no way to return. The re-entry corridor was narrow. The margin for error was measured in fractions of a degree. Less than 2 degrees, too steep or too shallow, and the crew would be lost. 12 successful Apollo missions returned to Earth. 12 times the heat shield worked. 12 times the crew survived re-entry. But it could have gone wrong. Any number of things could have failed. The lunar module. The LM, pronounced LEM. This was the spacecraft that actually landed on the moon. It looked like a spider. Thin legs, angular body, gold and black thermal insulation wrapped around the structure. Windows at odd angles, antennas sticking out in all directions. It looked fragile. It looked like it would fall apart if you touched it. In some ways, it was fragile. The skin of the lunar module was thinner than aluminum foil in places. So thin, you could puncture it with a screwdriver if you weren't careful. Engineers joked that you could poke your finger through the wall. But it didn't need to be strong. The LM was designed to operate only in the vacuum of space. It never had to deal with atmospheric drag or aerodynamic forces. So it didn't need to be streamlined or heavily built. It could be ugly as long as it was functional. And it was functional. The descent stage stayed on the moon. After the astronauts finished their surface activities and climbed back into the LM, they didn't need the descent stage anymore. So they left it behind. The descent stage became a permanent fixture on the lunar surface, along with the landing legs and any equipment the astronauts had unloaded. All 6 Apollo landing sites still have descent stages sitting there, slowly being pitted by micrometeorite impacts, but otherwise unchanged. The ascent stage was the top half of the lunar module. This contained the crew cabin and the ascent engine that would lift the astronauts back to lunar orbit. The ascent engine had to work perfectly. There was no backup. If the ascent engine failed to ignite, the astronauts were stranded on the moon. There was no rescue mission. No way to send another spacecraft to bring them home. They would die on the lunar surface when their oxygen ran out. President Nixon had a speech prepared for this scenario. A speech to be delivered if astronauts were stuck on the moon, unable to return. The speech talked about how these brave men would be remembered, how they gave their lives in the pursuit of knowledge, how their sacrifice would inspire future generations. It was a beautiful speech. Fortunately, Nixon never had to give it. The ascent engine fired successfully on every Apollo mission. Every crew that landed on the moon made it back to orbit. Landing on the moon itself was terrifying. The most dangerous part of the entire mission. The lunar module descended from orbit, firing its engine to slow down. The descent took about 12 minutes from the start of powered descent to touchdown. 12 minutes, where everything had to go perfectly. The LM started in a circular orbit about 60 miles, or 100 kilometers, above the lunar surface, moving at roughly 3,600 miles per hour, or 5,800 kilometers per hour. To land, it had to slow down almost to a standstill and descend 60 miles vertically. The astronauts couldn't see where they were landing until the very last moment. The LM descended feet first, with the crew facing upward. They were flying backward and downward toward the lunar surface, watching the stars and Earth, not the ground. They had to trust the computer. The lunar module guidance computer had roughly 72 kilobytes of memory, less than a single email attachment today. But it was enough. The computer tracked the LM's position, calculated the optimal descent trajectory, and fired the engine at precise intervals to keep the spacecraft on course. About 7,000 feet above the surface, or 2,100 meters, the computer pitched the LM forward. Finally, the astronauts could see the ground. And often, what they saw was bad. Craters, boulders, slopes too steep to land on safely. The computer was guiding them toward a programmed landing site based on orbital photographs. But if the site was actually unsuitable, the astronauts had to take over. Neil Armstrong famously had to take manual control during the Apollo 11 landing. The computer was guiding him toward a boulder field. Huge rocks scattered across the surface. Landing there would have been catastrophic. So Armstrong took control. He used the hand controller to pitch the LM forward, flying horizontally over the boulder field, searching for a clear spot. The computer displayed warnings. The fuel was running low. Each second of flight burned precious propellant. Mission Control was watching the fuel gauge. They started calling out the remaining time. 60 seconds. 30 seconds. Alarms were blaring in the cabin. Program alarms, indicating the computer was overloaded, trying to process too much information. Armstrong ignored them. He focused on finding a landing spot, scanning the surface through the window, looking for clear ground. 20 seconds of fuel left. He saw a small crater with a relatively flat area beyond it. He flew toward it. 10 seconds. He started the final descent. Dust kicked up by the engine began obscuring the surface. He couldn't see the ground directly beneath the LM anymore. He had to estimate the distance based on rocks and shadows at the edge of the dust cloud. 5 seconds. The LM touched down. Engine shut down. Armstrong's first words were not poetic. They were technical. Contact light. One of the probes extending below the landing legs had touched the surface, triggering a light on the control panel. He shut down the engine immediately. The LM settled onto the surface. And then, only then, came the famous phrase, "Tranquility Base, here. The Eagle has landed." Mission Control erupted in cheers. Later analysis showed Armstrong had landed with less than 25 seconds of fuel remaining. If he'd taken 5 more seconds to find a landing spot, he would have had to abort. The mission would have failed. Other Apollo landings had similar challenges. Apollo 12 landed in a dust storm kicked up by the descent engine. Pete Conrad couldn't see the surface for the last few seconds. He landed based on instruments and memory, estimating where the ground should be. The LM touched down harder than planned, jolting the crew. But it held together. Every landing was different. Every landing had its own challenges. Every landing required split-second decisions by the astronauts. And every landing could have failed. The margins were that thin. Attached to the command module was the service module, a cylindrical section about 24 feet long and 13 feet in diameter. It contained everything the astronauts needed to survive and maneuver in space. Life support systems that recycled air and removed carbon dioxide. Fuel cells that generated electricity by combining hydrogen and oxygen. The main engine used for major maneuvers, like leaving lunar orbit and starting the journey home. Propellant tanks holding fuel for that engine. Thrusters for minor course corrections and attitude control. Radiators to dissipate heat into space. The service module was unpressurized. Astronauts couldn't access it during flight. It was purely a utility section, but it was critical. The fuel cells provided all the electrical power for the spacecraft. 3 fuel cells, each combining hydrogen and oxygen to produce electricity and water. The chemical reaction was simple. 2 hydrogen molecules plus 1 oxygen molecule produces 2 water molecules and electrical current. The water was used for drinking and cooling. The electricity powered all the systems. Life support, communications, computers, instruments, everything. If the fuel cells failed, the spacecraft would die. No power meant no life support, no guidance, no communications. The crew would have only batteries for backup, enough for a few hours at most. The service module engine, called the Service Propulsion System, or SPS, was the spacecraft's main propulsion. It produced 21,000 pounds of thrust. Not much compared to the Saturn V's engines, but enough to change the spacecraft's velocity significantly. The engine had to fire multiple times during a mission, once to slow down and enter lunar orbit, once to leave lunar orbit and head back to Earth, sometimes for course corrections during the journey. Each burn had to be precise. Too long or too short, and the spacecraft would end up on the wrong trajectory. The engine used hypergolic propellants, 2 chemicals that ignite spontaneously when they contact each other. No ignition system needed. Just open the valves and the propellants mix in the combustion chamber and ignite. This made the engine extremely reliable. No spark plugs to fail. No ignition sequence to go wrong. As long as the propellants flowed, the engine fired. But it also meant the propellants were incredibly toxic and corrosive. Ground crews handling them had to wear protective suits. Any leak would be catastrophic. The service module also carried consumables. Oxygen for breathing, stored in high-pressure tanks. 2 tanks, each holding several hundred pounds of supercritical oxygen. Oxygen cooled to very low temperatures and kept under high pressure so it stays in a liquid-like state. This allowed more oxygen to be stored in less volume than gaseous oxygen at normal pressure. But it was also dangerous. The tanks were essentially bombs waiting to happen. Any spark, any contamination could cause an explosion. That's what happened on Apollo 13. One of the oxygen tanks had a damaged wire. During a routine procedure to stir the tank's contents, the damaged wire sparked. The spark ignited Teflon insulation. The fire superheated the oxygen. Pressure spiked. The tank exploded. The blast tore apart the service module's outer skin. Oxygen vented into space. The second tank started leaking. Within hours, both tanks were empty. No oxygen meant no fuel cells. No fuel cells meant no power. The service module was dying. And the command module, while it had its own oxygen supply, didn't have enough power generation to sustain the crew for the 4-day trip back to Earth. The crew had to shut down the command module to conserve its batteries and move into the lunar module, using it as a lifeboat. The explosion had torn a whole panel off the service module. When the crew jettisoned it and saw the damage, they realized how close they'd come to disaster. If the explosion had been slightly different, if it had breached the command module's cabin, they would have died instantly. If it had damaged the heat shield, they would have burned up during re-entry. They were lucky. Incredibly lucky. The service module also had cooling systems. The spacecraft generated heat from electronics, from the crew's bodies, from sunlight hitting the hull. In space, there's no air to carry heat away. You can't cool something by blowing air on it, because there's no air. You have to use radiators, panels that radiate heat away as infrared energy. The Apollo spacecraft had radiators on the service module. Coolant circulated through the spacecraft, absorbing heat, then flowing through the radiators where the heat was radiated into space. If the cooling system failed, the spacecraft would overheat. Electronics would fail. The crew would cook. Temperatures inside the cabin would rise to lethal levels within hours. So the cooling system was critical. And like everything else, it had to work perfectly for the entire mission. But the service module was jettisoned before re-entry. It burned up in the atmosphere. Only the command module, with the crew inside, made it back to Earth. This meant everything in the service module, all the equipment and systems, was used once and destroyed. More hardware thrown away. More costs that made the Apollo program unsustainable for the long term. Every landing was different. Once on the surface, the astronauts didn't immediately exit the LM. They had a checklist, pages of procedures to follow. After several hours, they began preparations for the first spacewalk. The Apollo spacesuit was a marvel of engineering. Multiple layers of fabric and insulation. The suit weighed about 180 pounds on Earth, or 82 kilograms. On the Moon, with 1/6 gravity, it felt like 30 pounds. But it was still bulky and restricting. The suit was also the only thing between the astronaut and the vacuum of space. If it failed, if a seal leaked or a hose ruptured, the astronaut would die in seconds. They depressurized the lunar module cabin. Opening the hatch required equalizing the pressure inside and outside. They vented the cabin's atmosphere into space. The first astronaut backed out of the hatch, feeling with his feet for the ladder. Neil Armstrong descended the ladder slowly. His movements were cautious, deliberate. Halfway down, he pulled a cord that deployed a camera on the side of the LM. The camera started broadcasting live images to Earth. grainy black-and-white video, but clear enough to show Armstrong descending. Over 600 million people watched. The most viewed live event in human history at that point. Armstrong reached the bottom of the ladder. He paused on the landing pad. Then he stepped off onto the lunar surface. One small step for man. One giant leap for mankind. The words were slightly garbled by static. He'd meant to say one small step for a man, but the word got lost in transmission. It didn't matter. Everyone understood what he meant. Humanity had reached another world. Armstrong's first impression of the lunar surface was the dust. Fine, powdery, clinging to everything. His boots sank in slightly, leaving crisp footprints. Walking felt strange. Each step launched him higher than expected. He had to learn a new gait, a kind of bouncing hop that covered ground efficiently. Then Buzz Aldrin came down the ladder. They got to work. The first moonwalk lasted about 2.5 hours. They had a long list of tasks. Deploy experiments. Collect rock and soil samples. Take photographs. Plant the American flag. The flag was one of the most important tasks from a public relations perspective. Planting the flag on the moon symbolized American achievement. Proof that America had won the space race. Those images became iconic. They've been reproduced millions of times. They represent American achievement and human exploration. Later missions brought the Lunar Roving Vehicle, the LRV, a battery-powered car designed to operate in the moon's environment. The rover folded up for storage on the LM and deployed after landing. It was a remarkable piece of engineering. Built by Boeing, it weighed about 460 pounds on Earth, or 209 kilograms. On the moon, with 1/6 gravity, it weighed about 77 pounds. The frame was made of aluminum tubing, lightweight but strong enough to carry 2 suited astronauts plus equipment. The wheels were unique. They couldn't use rubber tires because rubber becomes brittle in the extreme cold of the lunar night. Instead, the wheels were made of woven wire mesh, like chainmail. Each wheel had its own electric motor powered by batteries. The rover could drive in any direction, forward, backward, or sideways, by varying the speed and direction of each wheel independently. Top speed was about 8 miles per hour, or 13 kilometers per hour. That might not sound fast, but on the moon's surface, with rocks and craters everywhere, it felt plenty fast. The rover had no suspension in the traditional sense. The wire mesh wheels flexed to absorb bumps. The seats had minimal padding. Astronauts described the ride as rough, bouncing over rocks and crater rims. Navigation was primitive. A compass wouldn't work because the moon has no magnetic field. GPS didn't exist yet. So the rover used dead reckoning. It tracked wheel rotations and steering angle to estimate position. Not very accurate. The estimated position could be off by hundreds of feet after driving a few miles. So astronauts had to navigate by landmarks, keeping the LM in sight as much as possible. If the rover broke down far from the landing site, they'd have to walk back, in bulky spacesuits, carrying equipment, in the blazing sun or pitch darkness, depending on where they were in the lunar day. NASA had strict rules about how far astronauts could drive from the LM. They could never go farther than they could walk back with their remaining oxygen supply. This limited the range to about 6 miles from the landing site. But even within that range, they covered significant ground. Apollo 15 drove 17 miles total across 3 moonwalks. Apollo 16 drove 16 miles. Apollo 17 drove 22 miles. They explored craters, mountains, valleys. They collected samples from diverse locations, giving scientists a much better understanding of lunar geology than the walking missions could provide. The rover also carried a high-gain antenna that could be pointed at Earth. This allowed the astronauts to transmit live television from their traverses. People on Earth could watch, in real time, as astronauts drove across the lunar surface. The images were grainy and black and white, but they were incredible. Seeing the lunar landscape from the rover's perspective, watching the astronauts work, hearing their conversations, it brought the moon landings to life in ways the earlier missions couldn't. The rover's battery power was limited. After about 4 hours of driving and working, the batteries would be depleted. The astronauts had to return to the LM before that happened. Running out of power far from the landing site would have been catastrophic. Walking back would take hours. They might not have enough oxygen in their suits. So they carefully monitored battery levels and planned their routes to ensure they'd make it back in time. The rovers are still on the moon, parked near the landing sites where the astronauts left them. Batteries long dead, dust covered, but structurally intact. The wire mesh wheels haven't degraded. The aluminum frame hasn't corroded because there's no oxygen or water to cause corrosion. Future lunar visitors could theoretically find them and see them exactly as the Apollo astronauts left them over 50 years ago. The scientific work on the moon was extensive. Astronauts collected rock and soil samples, hundreds of pounds total across all missions. The lunar rocks turned out to be extraordinary. They're similar to Earth rocks in some ways, made of familiar minerals. Feldspar, pyroxene, olivine, the same minerals that make up Earth's crust and mantle. But they're also profoundly different. Lunar rocks have no water. Not a trace. Not a single water molecule trapped in the crystal structures. They formed in an environment completely devoid of moisture. This was one of the first major discoveries. On Earth, almost all rocks contain at least some water, either chemically bound in minerals or present as tiny inclusions. But lunar rocks are bone dry. This told scientists that the moon formed in an extremely hot environment where any water would have evaporated instantly. They've been exposed to solar wind for billions of years. Tiny particles from the sun, protons and helium nuclei, traveling at hundreds of miles per second, have been bombarding the lunar surface since the moon formed. These particles embed themselves in the surface minerals, penetrating a few micrometers deep. By analyzing the isotopes of helium and hydrogen trapped in lunar rocks, scientists can study the composition of the solar wind over billions of years. This provides a record of how the sun's output has changed over geological time. Information we can't get any other way. They're pitted by micrometeorite impacts. The moon has no atmosphere to burn up incoming debris. Every tiny grain of dust from space hits the surface at orbital velocity, tens of thousands of miles per hour. Even microscopic particles create tiny craters when they impact. Over millions of years, this creates a surface texture unlike anything on Earth. The rocks are covered in tiny glass beads. These beads form when micrometeorite impacts melt small amounts of rock, creating droplets of molten material that cool into spherical glass beads before they hit the ground. The beads are typically less than 1 millimeter in diameter. Under a microscope, they're beautiful, perfect little spheres of colored glass. The oldest lunar rocks are over 4 billion years old. Some samples from the lunar highlands are 4.4 billion years old, nearly as old as the solar system itself. Older than almost any rock found on Earth. Earth's geology is active. Plate tectonics recycle old rocks back into the mantle where they melt and reform. Weathering erodes surface rocks. Volcanic activity creates new rocks. So very few ancient rocks remain on Earth's surface. The oldest Earth rocks are about 4 billion years old, and they're rare. Most rocks on Earth's surface are much younger, hundreds of millions of years old or less. But the Moon is geologically dead. No plate tectonics. No erosion by wind or water. No volcanic activity for billions of years. Its surface preserves the early history of the solar system like a frozen record. Studying lunar rocks told us about the Moon's formation. Before Apollo, there were 3 main theories about how the Moon formed. The fission theory proposed that the Moon split off from Earth early in its history, torn away by rapid rotation. The capture theory suggested that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity when it passed too close. The co-formation theory said that Earth and the Moon formed together from the same cloud of material orbiting the young Sun. None of these theories quite fit the observations. The lunar rock samples provided the evidence needed to solve the mystery. The rocks showed that the Moon's composition is similar to Earth's mantle, but different from Earth's core. The Moon has very little iron compared to Earth. Earth has a large iron core that makes up about 1/3 of its mass. The Moon's core, if it has one, is tiny, less than 5% of its mass. This ruled out the co-formation theory. If Earth and the Moon formed together from the same material, they should have similar compositions. The capture theory had other problems. The chances of Earth capturing an object as large as the Moon are astronomically small, and the Moon's orbit is almost perfectly circular and almost perfectly aligned with Earth's equator. A captured object would have a much more eccentric orbit at a random inclination. The fission theory couldn't explain where the energy came from to spin Earth fast enough to throw off a moon-sized chunk of material. So, scientists developed a new theory, the giant impact theory. This theory proposes that early in Earth's history, about 4.5 billion years ago, a Mars-sized object called Theia collided with Earth. The impact was cataclysmic. Theia was traveling at several miles per second when it hit. The collision vaporized Theia and a large portion of Earth's mantle. The cores of both objects merged, sinking to become Earth's core. But the vaporized mantle material was ejected into orbit around Earth. This debris disk was incredibly hot, thousands of degrees. Hot enough that any water or other volatile compounds evaporated and escaped into space. Over time, the debris in orbit coalesced due to gravity, forming the Moon. Because the Moon formed from Earth's mantle material, it has a similar composition. But because it formed from vaporized material where volatiles escaped, it has no water and a very small core. This theory explains all the observations. The Moon's composition, its lack of water, its small core, its orbit aligned with Earth's equator. Everything fits. And the evidence came from those lunar rock samples. Scientists also discovered that the moon was volcanically active in the past. The dark areas visible from Earth, called Maria, are ancient lava flows. Billions of years ago, impacts created huge basins on the moon's surface. Later, magma from the moon's interior welled up and filled these basins, creating vast plains of solidified lava. The Apollo missions collected samples from both the highlands, the lighter-colored ancient terrain, and the Maria, the darker, younger lava flows. By dating these samples using radioactive isotopes, scientists determined that the Maria formed between 3 and 4 billion years ago. After that, the moon's volcanic activity ceased. The interior cooled enough that magma could no longer reach the surface. The moon became geologically dead. The Apollo samples also revealed the violent history of the early solar system. The lunar highlands are heavily cratered, scarred by billions of years of impacts. By counting craters and dating rock samples, scientists reconstructed a timeline of bombardment. About 4 billion years ago, the inner solar system experienced what's called the Late Heavy Bombardment, a period lasting about 200 million years, when the rate of impacts spiked dramatically. Asteroids and comets rained down on the inner planets. Earth, Mars, Venus, Mercury, and the Moon were all pummeled. The evidence is preserved on the Moon's surface because there's no erosion to erase it. On Earth, the craters from this period have long since been erased by plate tectonics and weathering. But on the Moon, they remain. The late heavy bombardment may have delivered water to Earth. Comets are largely made of ice. When they impacted Earth, they brought water with them. Some scientists think most of Earth's water came from comets during this period. We don't know for sure. But the lunar samples gave us the timeline of when it happened. None of this was known before Apollo. The Moon's origin was a mystery. Its geological history was speculation. The timeline of the solar system's early violence was unknown. The samples brought back solved these mysteries. They revolutionized our understanding of how rocky planets form and evolve. That alone justified the cost of the missions from a scientific perspective. But science wasn't the main goal. The main goal was political. The science was a bonus. Then they left. They climbed back into the ascent stage of the lunar module. They fired the ascent engine, which had to work perfectly because there was no backup. The ascent engine fired every time. Every Apollo mission that landed on the Moon successfully returned to orbit. They docked with the command module, transferred the crew and the rock samples, jettisoned the ascent stage, and fired the service module engine to break out of lunar orbit and begin the journey home. 3 days later, they splashed down in the Pacific Ocean, the only part of the spacecraft still intact. And they were heroes. The entire world watched. But the triumph masks just how dangerous the whole enterprise was. Every Apollo mission carried astronauts closer to death than most people realize. The risks were extraordinary. Apollo 1 never made it off the launch pad. January 27, 1967. A routine test. The crew, Gus Grissom, Ed White, and Roger Chaffee, were sealed inside the command module atop the Saturn Ib rocket. Not fueled, not ready to launch. Just a test of the spacecraft systems. A plugs-out test, meaning the spacecraft was running on internal power rather than ground support equipment. This was supposed to simulate the final countdown before launch. The cabin was pressurized with pure oxygen at slightly above atmospheric pressure. This was standard procedure for Apollo. Pure oxygen meant simpler life support systems. No need to carry nitrogen. Less weight. But pure oxygen is incredibly dangerous. Everything burns in pure oxygen. Materials that are flame-resistant in normal air burst into flames in pure oxygen. At 5:31 p.m., an electrical arc sparked somewhere in the wiring beneath Grissom's seat. The spark ignited the nylon netting and Velcro that covered much of the cabin interior. In the pure oxygen environment, the fire spread instantly. Within seconds, the entire cabin was an inferno. Temperatures exceeded 1,400 degrees Fahrenheit, or 760 degrees Celsius. The crew tried to open the hatch, but the hatch opened inward. The fire increased cabin pressure. The pressure differential made it impossible to open the hatch against that force. Ed White, the strongest of the three, grabbed the ratchet used to unlock the hatch. He strained against it with all his strength. It wouldn't budge. The fire consumed the oxygen faster than the crew could breathe. They suffocated within 30 seconds. Rescuers outside heard the crew's last transmissions. Fire. I smell fire. Fire in the cockpit. We've got a bad fire. We're burning up. Then silence. It took 5 minutes for rescuers to open the hatch from outside. By then, all 3 astronauts were gone. The investigation revealed shocking negligence. The command module was filled with flammable materials. Nylon, Velcro, paper checklists, plastic switches. All of it burned readily in pure oxygen. The wiring was poorly insulated, prone to shorts and arcing. The hatch design was fatally flawed. NASA knew about these problems. Engineers had raised concerns. But schedule pressure and cost-cutting led to corners being cut. 3 men paid the price. The Apollo program shut down for 20 months, while NASA redesigned the command module. They removed flammable materials, improved wiring insulation, redesigned the hatch to open outward in 1.5 seconds, changed the cabin atmosphere to 60% oxygen, 40% nitrogen during ground operations. The changes worked. No other Apollo crew died in a cabin fire, but the Apollo 1 disaster showed how thin the margin was between success and catastrophe. How easily things could go wrong. How quickly death could come. Every launch carried similar risks. Apollo 12 was struck by lightning twice during launch. 36.5 seconds after liftoff, lightning hit the rocket. Every electrical system in the command module shut down. Fuel cells offline. Guidance platform tumbled. Instrumentation dead. The crew was flying blind. Alarms blaring. Warning lights flashing across every panel. In the blockhouse, flight controllers saw telemetry drop out. They had no idea what was happening. The rocket was still flying, still accelerating. The Saturn V's automatic systems were unaffected, but the spacecraft on top was crippled. If the crew aborted now, they'd have to separate from the rocket while it was still under power. The escape tower would yank the command module away. But the violence of the abort might kill them, and the Saturn V, unpiloted, would crash somewhere in the Atlantic. Mission Control had seconds to decide: abort or continue. Pete Conrad, the commander, made the decision. We're going to ride it out. John Aaron, a young flight controller, remembered a similar failure in a simulation. He remembered an obscure switch setting that might restore power. Flight. Try SCE to AUX. SCE to auxiliary. Signal conditioning, electronics to auxiliary power. Alan Bean, the lunar module pilot, found the switch. He didn't know what it did. None of the crew had ever used it, but he threw it. The displays came back online. Telemetry resumed. The spacecraft was alive again. But the guidance platform was still tumbled. The inertial measurement unit had lost its orientation. Without that, the spacecraft couldn't navigate. They continued to orbit anyway. Once in space, the crew realigned the guidance platform using star sightings, a procedure that normally took an hour. They did it in minutes. Everything worked. The mission continued. They landed on the moon. But it could easily have ended differently if Bean hadn't found that switch. If the second lightning strike, 52 seconds after launch, had damaged something critical. If the guidance platform couldn't be realigned, the mission would have been aborted. Or worse, the crew might have been lost. Lightning shouldn't strike rockets. Launch windows are chosen to avoid thunderstorms. But Apollo 12 launched into marginal weather. Schedule pressure. Political pressure to maintain the timeline. They launched anyway, and nearly paid for it. Apollo 13's explosion could have killed the crew in dozens of ways. The blast itself could have breached the command module. Instant decompression. The astronauts would have had seconds before unconsciousness. Minutes before death. The explosion could have damaged the heat shield. They wouldn't have known until re-entry. And then it would have been too late. The fire would have consumed them before they realized what was wrong. The explosion could have destroyed the lunar module. Without the LM to use as a lifeboat, the crew would have died within hours when the command module's power ran out. The fact that none of these things happened was luck. Extraordinary luck. The explosion happened in exactly the right place to disable the service module without destroying the command module or lunar module. If it had happened a few hours later, after the crew had separated the LM for the landing, they would have had no lifeboat. If it had happened during the return journey, after they'd jettisoned the LM, they would have had no backup. The timing was crucial, and it was pure chance. Every phase of every mission carried mortal dangers. Launch could end in explosion. The Saturn V was a controlled bomb. Millions of pounds of fuel and oxidizer kept separate by thin metal walls and valve seals. If those walls failed, if those seals leaked, the propellants would mix and detonate. The rocket would explode with the force of a small nuclear weapon. This happened to other rockets. Soviet N-1 explosions. American rockets exploding on the pad or shortly after launch. It could have happened to Saturn V. It never did. But it could have. The journey to the moon carried radiation risks. Outside Earth's magnetic field, astronauts were exposed to cosmic rays. High-energy particles from deep space, traveling at nearly the speed of light. When these particles hit human tissue, they cause damage at the cellular level. Increased cancer risk. Potential sterility. Neurological effects. The Apollo missions were short enough that the exposure was manageable, but a solar flare could have changed that. The sun occasionally releases bursts of high-energy particles, solar flares that flood the space between Earth and Moon with radiation. If a major flare had occurred while astronauts were on the lunar surface or in transit, they could have received lethal doses. Their spacesuits provided minimal shielding. The command module's walls were thin aluminum, barely better. A truly massive flare could have killed them before they could return to Earth. NASA monitored solar activity constantly. They would have aborted a mission if a major flare seemed imminent. But solar weather is unpredictable. Flares can erupt with little warning. The astronauts were lucky. No major solar events occurred during any Apollo mission. But they could have. The Moon itself was dangerous. The lunar surface temperature swings wildly. In sunlight, 250 degrees Fahrenheit or 121 degrees Celsius. In shadow, minus 250 degrees Fahrenheit or minus 157 degrees Celsius. A 500-degree swing. The spacesuits had to handle both extremes. If the cooling system failed while an astronaut was in sunlight, they would overheat within minutes. Heat stroke in a spacesuit, in the vacuum of space, on the Moon. No way to cool down except to get back to the LM. If they couldn't make it in time, they would die. If the heating system failed while in shadow, they would freeze. Again, no way to warm up except to return to the LM. The suits worked perfectly. No failures. But the potential was there. A damaged spacesuit meant death. The suits were tough, but not indestructible. Tears were possible. Apollo 12's Pete Conrad tore his suit on a sharp edge inside the LM. He was lucky. The tear didn't penetrate the pressure layer. Just the outer protective layer. They patched it with duct tape. But if the tear had been deeper, if it had breached the pressure bladder, Conrad would have had minutes to get back inside the LM before his oxygen ran out. If he'd been far from the LM when it happened, he wouldn't have made it. The lunar module landing could have failed in countless ways. Engine failure during descent. Computer failure. Guidance system failure. Running out of fuel before touchdown. Landing on a boulder or in a crater too steep. Tipping over after landing. Any of these would have meant aborting the landing or stranding the crew on the surface. The ascent engine had to fire perfectly. One engine. No backup. No redundancy. No second chance. If it failed to ignite, the astronauts died on the Moon. Simple as that. No rescue possible. No way to send another lander to get them. They would have had a few hours of oxygen. Then nothing. President Nixon's speech would have been delivered. The nation would have mourned. But the astronauts would still be gone. The ascent engine worked every time, but it didn't have to. Docking with the command module after lunar liftoff was manual. The LM pilot flew the ascent stage toward the command module. The commander operated the docking mechanism. If they missed, they had to try again. But fuel was limited. Only enough for a few attempts. If they couldn't dock after multiple tries, they'd run out of fuel. The LM would drift away from the command module. The crew would die when their oxygen ran out. The command module pilot would be alone. He'd have to return to Earth without his crewmates. Knowing they were still alive, adrift in lunar orbit, waiting to die. This scenario was practiced extensively. The crews trained for it until docking became routine. But the possibility of failure was real. Re-entry was the final gamble. Falling through Earth's atmosphere at 25,000 miles per hour. Protected only by a heat shield a few inches thick. If the shield failed, the crew would burn up. If the entry angle was too steep, they'd be crushed by deceleration forces. If the entry angle was too shallow, they'd skip off the atmosphere and tumble into space. No second chance. No abort option. Either the re-entry worked or it didn't. The heat shield worked every time. The entry angle was correct every time. But it didn't have to be. 12 successful missions. 12 times, everything worked. 12 times, the astronauts came home alive. The success rate makes it seem routine. But it wasn't routine. Every mission was a roll of the dice. Every phase carried mortal risk. The astronauts knew it. They went anyway. Because the goal was worth it. Because they believed in the mission. Because someone had to go first. And they were willing to be that someone. The entire world watched. 12 humans walked on the moon across 6 Apollo missions. Every crew that landed made it back safely. Every mission achieved its objectives. Humanity's greatest achievement. And then it ended. Not because we'd learned everything there was to learn. Not because we'd exhausted the possibilities. But because the political moment that enabled it passed. The Cold War space race ended. The funding dried up. The public moved on. And the moon became history instead of the future. Going back to the moon now is actually harder than it was in the 1960s. Not technologically. We have better computers, better materials, better understanding. But institutionally, politically, financially, it's far more difficult. Because everything we built to go to the moon in the 1960s is gone. The Saturn V rockets are museum pieces. 3 of them are on display. One at Kennedy Space Center in Florida. One at Johnson Space Center in Texas. One at the U.S. Space and Rocket Center in Alabama. You can walk underneath them and marvel at their size. But they're museum exhibits. Historic artifacts, not functional rockets. The production lines are dismantled. The factories that built the F-1 engines are gone, converted to other purposes, or demolished entirely. The tooling that shaped the fuel tanks no longer exists. The jigs that held components during assembly were scrapped decades ago. The engineers who designed those systems are retired or deceased. The average age of an Apollo engineer was mid-20s to early 30s during the program. That was 50 years ago. Most of them are in their 70s or 80s now. Many have passed away. The hands-on knowledge, the tricks and techniques that weren't written down are gone with them. The institutional knowledge has been lost. Companies that manufactured components for Apollo don't exist anymore. They were bought out, merged, restructured, or went bankrupt. The supply chains are gone. In the 60s, NASA could call on thousands of specialized contractors. Machine shops that could fabricate rocket components to exact specifications. Chemical companies that could produce exotic propellants. electronics firms that could build custom guidance systems. Many of those capabilities no longer exist. Modern manufacturing has evolved. We use different processes, different materials, different technologies. Recreating Apollo-era components with modern techniques is possible. But it's not straightforward. It's not a matter of pulling old blueprints off the shelf and following them. The blueprints exist. NASA archived everything. Tens of thousands of pages of technical drawings. Specifications for every component. Procedures for every operation. But the blueprints assume knowledge and capabilities that no longer exist. They reference tools that were scrapped, processes that are obsolete, materials that aren't manufactured anymore. To build a Saturn V today would require reverse engineering the entire production process. Figure out how to manufacture each component using modern techniques. Find substitutes for materials that are no longer available. Test everything to make sure it works. That would cost billions of dollars. And there's no guarantee it would work as well as the original. The Saturn V was developed through iterative testing and refinement. Engineers built prototypes, tested them, found problems, fixed them, tested again. This process took years. Thousands of tests, large and small. Each test revealed issues that needed addressing. To recreate that process today would require similar investment in time and resources. And modern safety standards are far stricter than in the 60s. NASA can't take the risks they took during Apollo. Public tolerance for failure has decreased dramatically. If astronauts died during a modern moon mission, the political fallout would be enormous. The program would likely be cancelled immediately. Congressional investigations, media scrutiny, public outrage. The agency's budget would be slashed. Future missions would be grounded. So NASA has to be far more cautious. Testing has to be exhaustive. Every component tested individually. Every system tested as part of the whole. Multiple redundancies built in. Abort options at every stage. Backup systems for backup systems. This makes missions slower and more expensive. Apollo 11 launched less than 2 years after Apollo 1. NASA redesigned the command module, tested it, and got back to flying in 20 months. That timeline would be impossible today. A similar accident now would ground the program for 5 years or more. Not because the technical problems would be harder to solve, but because the political and regulatory processes would take longer, and because NASA would have to prove, beyond any doubt, that the problems were fixed. Then there's the question of why go at all? In the 1960s, the answer was clear. Beat the Soviets. Win the Cold War. Demonstrate American technological superiority. That motivation no longer exists. The Soviet Union collapsed in 1991. The Cold War is over. Russia has a space program, but it's not the rival it once was. Budget constraints have limited their ambitions. They haven't sent a probe beyond Earth orbit in years. China is a different story. China has an ambitious and well-funded space program. They've landed robotic probes on the moon. Chang'e 4 landed on the far side of the moon in 2019, the first spacecraft ever to do so. Chang'e 5 returned samples to Earth in 2020. the first new lunar samples in over 40 years. China has built a space station in orbit, Tiangong, operational since 2021, and they've stated intentions to land astronauts on the moon. Their timeline suggests sometime in the 2030s, maybe earlier if their program accelerates. If China lands astronauts on the moon before America returns, it will be significant. Not the same as the Apollo-era space race. There's no Cold War context. The ideological stakes aren't as high, but it would shift perceptions. China would be seen as the ascendant space power. America would be seen as stagnant, unable to repeat what it did 50 years ago. That perception could motivate increased funding for Artemis. National pride is still a powerful force, but it's not a guarantee. The American public is more divided now than during the Cold War. Not everyone sees competition with China as important. Not everyone thinks space exploration should be a priority. NASA has to justify the expense using other arguments. Scientific research. The moon is a unique laboratory. Low gravity, no atmosphere, ancient surface. Experiments that can't be done on Earth. Studies of solar wind, cosmic rays, geology. But most of those experiments can be done robotically. Robots are cheaper than humans. They don't need life support. They don't need to come back. They can operate in conditions that would kill humans instantly. The scientific return per dollar is often higher for robotic missions. So, why send humans? Resource utilization. The moon has water ice at the poles, hidden in permanently shadowed craters where sunlight never reaches. Temperatures in these craters are among the coldest in the solar system. Cold enough that ice has persisted for billions of years. This ice is scientifically interesting, but it's also potentially useful. Water can be split into hydrogen and oxygen. Oxygen for breathing, hydrogen and oxygen for rocket propellant. If you can extract and process this water on the moon, you can refuel spacecraft there. Instead of launching all propellant from Earth, you refuel at the moon. This changes the economics of deep space missions. Launching from Earth requires fighting Earth's gravity. Launching from the moon requires fighting only 1/6 that gravity. Fuel requirements are dramatically lower. A spacecraft refueled at the moon can travel much farther than one launched from Earth with the same initial mass. Mars missions become more feasible. Missions to the asteroid belt. Even missions to the outer planets. The moon becomes a gas station for the solar system. But extracting and processing lunar water requires infrastructure, mining equipment, processing facilities, power systems, storage tanks. All of this has to be transported to the moon and set up, which requires numerous heavy lift launches, which costs billions of dollars. And the technology for extracting water from lunar regolith hasn't been fully developed yet. We know the ice is there, but we don't know exactly how much, how pure it is, how difficult it will be to extract. Robotic missions could answer those questions. Before committing to expensive human missions, it makes sense to send robots first. Drill some test wells. Analyze the ice. Prove the concept. NASA is planning to do this. But it takes time and money. Testing technologies is another justification. The moon is close enough that if something goes wrong, help is only a few days away. unlike Mars, which is months away at its closest. Using the Moon as a proving ground makes sense. Test life support systems. Test habitats. Test power generation. Test resource extraction. Test everything in a real environment before attempting the much riskier journey to Mars. This is a sound engineering approach, but it's also expensive. Building test facilities on the Moon costs almost as much as building operational facilities. And if the goal is Mars, why spend decades on the Moon? Why not develop the technologies on Earth and go directly to Mars? These are reasonable questions. NASA's answer is that the Moon is a necessary stepping stone. But not everyone agrees. Some argue for going directly to Mars. Others argue for focusing exclusively on robotic exploration. The debate continues. Then there's the geopolitical angle. Space is becoming increasingly important strategically. Satellites are critical infrastructure. Communications, navigation, weather forecasting, military reconnaissance. Modern society depends on space assets. China and Russia are developing anti-satellite weapons, missiles that can destroy satellites in orbit, lasers that can blind or disable them. The militarization of space is happening, whether we like it or not. Having a presence on the Moon could be strategically valuable. Early warning systems, communication relay stations, even missile defense installations. This sounds like science fiction, but military planners think in terms of decades. What seems far-fetched now might be standard in 20 years. The Outer Space Treaty of 1967 prohibits claiming sovereignty over celestial bodies. No nation can own the Moon. But the treaty doesn't prohibit economic activity. Mining, resource extraction, commercial operations, these are allowed. Several countries are developing legal frameworks for space resource rights. The US passed the Space Act of 2015, granting American companies property rights to resources they extract from asteroids or the Moon. Luxembourg passed similar legislation. The UAE has announced intentions to do the same. This creates a legal gray area. If a company extracts resources from the Moon, do they own those resources? Can they sell them? What happens if multiple countries or companies claim the same area? These questions haven't been resolved, but they will need to be if commercial lunar activity becomes reality. And commercial interest is growing. Several private companies are developing lunar landers. Astrobotic, Intuitive Machines, SpaceX, Blue Origin. They see business opportunities. Transporting payloads to the Moon for governments and research institutions. Eventually, tourism. Taking wealthy individuals to lunar orbit or the surface. It sounds absurd. Who would pay millions of dollars to visit the Moon? But people have paid tens of millions to visit the International Space Station. There's a market for space tourism, however small. If costs can be reduced through reusable spacecraft and in situ resource utilization, lunar tourism might become economically viable. Not for everyone, but for the ultra-wealthy. And if that happens, it could drive sustained lunar presence in ways government programs never could. Private investment seeking profit is more sustainable than government programs dependent on political whims. But we're not there yet. The technology isn't ready. The costs are still prohibitive. The market is unproven. So, we're in a transitional period. Government programs like Artemis are leading the way. Private companies are developing capabilities. The infrastructure for sustained lunar presence is slowly being built, but it's not inevitable. Any number of things could derail it. A major accident during Artemis missions. A change in political leadership that deprioritizes space. Budget crises that force cuts. Technical challenges that prove insurmountable. Or simply, a collective decision that it's not worth it. That Earth's problems are more important than exploring the moon. That we should spend our resources here, not out there. The moon is 238,900 miles from Earth, or 384,400 kilometers. Close enough to see with the naked eye. Close enough to reach in 3 days with current technology. But far enough that getting there requires immense effort, immense cost, immense risk. It's not impossible. We've proven that. 12 humans have walked on its surface. But it's not inevitable. Going back requires making a choice. A choice to prioritize lunar exploration over other things. A choice to commit resources for years or decades. A choice to accept risks and setbacks and failures. That choice hasn't been made yet. Not fully. Artemis is a step, but it's not a commitment to sustained lunar presence. It's a program that could be cancelled if budgets get tight or political winds shift. History has shown that before. NASA's new moon program. Named after Apollo's twin sister in Greek mythology, Artemis is supposed to land astronauts on the moon again, this time including the first woman and the first person of color. The symbolism is deliberate. Apollo was the god of the sun. Artemis was the goddess of the moon. Where Apollo was male-focused, every astronaut who walked on the moon was a man. Artemis represents inclusivity. The program officially began in 2017. The Space Launch System, NASA's new heavy-lift rocket, is the cornerstone. It uses modified space shuttle main engines for its core stage. Incredibly powerful, incredibly expensive. Each launch costs over $2 billion. And the SLS is expendable, like the Saturn V. Used once and thrown away. Every launch requires building a new rocket. Artemis I, an uncrewed test flight of the Space Launch System rocket and Orion spacecraft, launched successfully in November 2022. It flew around the moon and returned to Earth. The rocket performed perfectly. The Orion spacecraft completed its mission flawlessly. The heat shield withstood re-entry temperatures of 5,000 degrees Fahrenheit, or 2,760 degrees Celsius. Everything worked. Artemis II launched in April 2026. This is the first crewed flight. 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen flew around the moon. Glover is the first African American to leave Earth orbit. Koch became the first woman to fly beyond Earth orbit. Hansen is the first Canadian beyond Earth orbit. They didn't land, just flew by and returned. It was a test of the systems with humans aboard, making sure life support worked, making sure the crew could operate the spacecraft, making sure radiation exposure was within acceptable limits. The mission lasted about 10 days from launch to splashdown in the Pacific Ocean. Artemis III is scheduled for mid-2027. But the mission profile changed dramatically in February 2026. Originally, Artemis III was supposed to be the first lunar landing. But NASA administrators made a critical decision. They pushed the landing back to Artemis IV. Artemis III will now test lunar landers in low Earth orbit, not at the Moon, in Earth orbit. The crew will launch aboard Orion and practice docking with commercial lunar landers from SpaceX and Blue Origin. They'll test spacesuit systems. New spacesuits designed specifically for lunar surface operations. More flexible than Apollo suits. Better mobility. Improved life support that can last 8 hours instead of 7. They'll validate procedures. Transfer from Orion to the lander and back. Operating lander systems. Emergency protocols. All in the safety of low Earth orbit, where if something goes wrong, they're only hours from help. It's similar to Apollo 9, which tested the lunar module in Earth orbit before Apollo 10 took it to the Moon. This represents a more cautious, methodical approach. NASA learned from Apollo 13 and the Space Shuttle disasters that rushing leads to catastrophe. Testing systems incrementally reduces risk, so they're taking their time, testing each piece before committing to the full mission. Artemis IV is now scheduled for early 2028. This will be the landing. The first time humans touch the lunar surface since Apollo 17 in December 1972. More than 55 years later, an entire generation will have passed. The landing site is planned for the lunar South Pole region, near Shackleton Crater. This area is scientifically valuable because it has permanently shadowed craters where water ice may exist. It also has peaks of eternal light, mountain ridges that receive almost constant sunlight year-round, perfect for solar power generation. A lunar base there could operate continuously without the 2-week lunar night that most of the Moon experiences. But even this is uncertain. The program is expensive. Development costs have exceeded expectations. Each Space Launch System launch costs over $2 billion. And the SLS is expendable, like the Saturn V, used once and thrown away. Every launch requires building a new rocket. This has drawn criticism. Private companies are developing reusable heavy-lift rockets that could potentially launch for a tiny fraction of the SLS's cost. The program exists at the mercy of political winds, of budget priorities, of public opinion. And unlike the 1960s, there's no existential motivation driving it forward. China has an ambitious space program. They've landed robotic probes on the Moon. They've stated intentions to land astronauts on the Moon. Their timeline suggests they might do it in the 2030s. If China lands astronauts on the Moon before America returns, it will be politically significant. But it won't be the same as the space race. There's no Cold War. The stakes aren't as high. Artemis faces challenges Apollo never did. It has to justify itself on scientific and economic grounds, not just political victory. It has to coordinate with international partners. It has to compete for budget with countless other priorities. Healthcare, infrastructure, climate change. Space exploration has to make its case every single year. And that case is harder to make than it was in the 1960s. The Moon is 238,900 miles from Earth, or 384,400 kilometers. Close enough to see with the naked eye. close enough to reach in 3 days with current technology, but far enough that getting there requires immense effort, immense cost, immense risk. It's not impossible. We've proven that. 12 humans have walked on its surface. But it's not inevitable. Going back requires making a choice. A choice to prioritize lunar exploration over other things. A choice to commit resources for years or decades. A choice to accept risks and setbacks and failures. That choice hasn't been made yet. Not fully. Artemis is a step, but it's not a commitment to sustained lunar presence. It's a program that could be cancelled if budgets get tight or political winds shift. History has shown that before. The Apollo program was never really about science. It was about political victory, to prove that we could, to beat the Soviets. And once we'd proven it, once we'd won, the motivation disappeared. The justifications we use now, science and resource extraction and testing technologies, are all valid. But they're not compelling enough to drive sustained investment. Not in the way Cold War rivalry was. So the moon waits. Over 50 years since the last human walked on the moon. A generation has lived their entire lives without witnessing a lunar landing. For people born after 1972, moon landings are history. Something their grandparents watched. Something that happened in the past. Not something happening now. Not something to look forward to. The moon has become something we did in the past, an achievement we look back on with pride and nostalgia, but not something we're actively doing. And that's strange when you think about it. We have better technology now. Computers, millions of times more powerful than what Apollo had. Materials science that would have seemed like magic in the 1960s. Rockets that can land themselves and fly again. We understand the lunar environment better. We've analyzed the Apollo samples for decades. We've mapped the surface in extraordinary detail. In every measurable way, we're more capable of going to the moon than we were in the 1960s. More knowledge. Better technology. More experience. And yet, we're not there. The reason isn't technological. It's not that we can't go back. It's that we haven't decided it's worth the cost. That decision, or rather the lack of decision, says something profound about us as a civilization. In the 1960s, we were willing to spend enormous sums to achieve a goal, to prove something to ourselves and the world, to demonstrate that the impossible was possible. We mobilized an entire nation, hundreds of thousands of workers, thousands of companies, universities, research institutions, government agencies, all focused on a single goal. Put a human on the moon before the end of the decade. We invented new technologies, new materials, new computers, new propulsion systems, things that didn't exist when Kennedy made his promise, things that had to be created from scratch. We took risks that seem reckless in retrospect. Apollo 1 killed 3 astronauts in a cabin fire during a ground test. NASA redesigned the command module and kept going. Apollo 13 nearly killed 3 more when an oxygen tank exploded en route to the moon. They made it home through improvisation and luck. NASA investigated, fixed the problems, kept flying. We lost astronauts in testing, crashes during training flights, equipment failures. But the program continued, because the goal mattered more than the cost, more than the risk. more than the criticism. The moon represented the future. It was the symbol of human achievement, of what we could accomplish if we pushed ourselves. Landing on the moon was seen as the beginning of a new era: space colonies, interplanetary travel, humanity spreading across the solar system and eventually beyond. It all seemed inevitable. We went to the moon, so surely we'd go to Mars next. Then to the moons of Jupiter and Saturn. Then to other star systems. The future was out there, among the stars, and we were on our way. But that didn't happen. We went to the moon 6 times and stopped. We've never gone beyond low Earth orbit since 1972. Over 50 years. More than half a century. An entire human lifetime. The International Space Station orbits just 250 miles above Earth. That's closer than the distance between New York and Boston. We can go higher, briefly, but we don't stay there. We don't live there. We don't build there. We orbit Earth and call it space exploration. The future we imagined didn't arrive. And that's disillusioning. It challenges the narrative of inevitable progress. The idea that humanity is destined to expand into space. That we're on a trajectory toward becoming a spacefaring civilization. Maybe we're not. Maybe the Apollo program was an anomaly. A unique moment in history when circumstances aligned to make the impossible possible. The Cold War created urgency. The space race created competition. Kennedy's deadline created focus. The political will created funding. All of these factors came together at exactly the right time. And when those circumstances changed, when the Cold War dynamics shifted, when Kennedy's deadline passed, when the Soviets gave up, the program ended. We reverted to the mean, to staying on Earth, to focusing on terrestrial problems. Maybe that's where we belong. Maybe space is too hard, too expensive, too dangerous for sustained human presence. Maybe robots should do the exploring. They don't need life support. They don't need to come back. They can go places humans can't. They can survive conditions that would kill us instantly. And they're far cheaper than crewed missions. The Mars rovers, Spirit, Opportunity, Curiosity, Perseverance. They've explored Mars for years, decades even. Opportunity operated for 15 years before finally succumbing to a dust storm. It traveled 28 miles across the Martian surface, sent back hundreds of thousands of images, analyzed countless rock samples, discovered evidence of ancient water, all for a fraction of what a crewed mission would cost. Voyager 1 and 2 launched in 1977. They explored Jupiter, Saturn, Uranus, Neptune. They're now in interstellar space, still sending data back nearly 50 years later. No human mission could have done that. We would have needed life support for decades. Food, water, air, radiation, shielding, propulsion to get there and back. The costs would be astronomical, impossible with current technology. But robots made it possible. These are legitimate arguments. There's a case to be made that human spaceflight is inefficient, that we could learn more and go farther by sending robots, that the money spent on crewed missions would be better spent on Earth, solving poverty, curing diseases, addressing climate change. These are real problems affecting billions of people right now. Spending hundreds of billions to send a few astronauts to the moon doesn't directly help anyone on Earth. It's a choice to prioritize exploration over immediate human needs. And reasonable people can disagree about whether that's the right choice. But there's another perspective. The perspective that says human spaceflight matters not because of what it achieves directly, but because of what it represents. The willingness to take on challenges that seem impossible, to push boundaries, to explore, not because it's easy or profitable, but because it's hard, because it expands our understanding of what's possible. The Apollo program inspired an entire generation. Kids who watched the moon landings grew up to become scientists, engineers, teachers. They were inspired by what humanity achieved, by the audacity of the goal and the determination to reach it. That inspiration has value. It's hard to quantify, but it's real. How many breakthroughs came from people who were inspired by Apollo? How many innovations were driven by the desire to reach for something beyond immediate practicality? We can't know, but it's not zero. Space exploration also drives technological development. The Apollo program, advanced computing, materials, science, telecommunications, medicine, miniaturized electronics to fit in spacecraft, developed new insulation materials that became everyday products, created communication satellites that revolutionized global connectivity, advanced medical monitoring that's now standard in hospitals. Technologies developed for space found applications on Earth. The economic multiplier effect is real. Every dollar spent on space exploration generates economic activity beyond the initial investment. But that's still a secondary justification. The primary question is philosophical. What kind of species do we want to be? One that stays on one planet because it's cheaper and safer? Or one that explores beyond our world despite the cost and risk? There's no objectively correct answer. It's a values question. Different people will answer it differently based on their priorities and worldviews. What we can say is that the choice we make defines us. If we choose to return to the moon, to establish a sustained presence there, to use it as a stepping stone to Mars and beyond, we're saying that exploration matters. That pushing boundaries is part of what makes us human. That the future isn't just something that happens to us, it's something we create. That we're not content to stay in one place forever. That there's something in human nature that drives us to explore, to discover, to reach beyond our current limits. If we choose not to go back, to focus exclusively on Earth, we're saying that immediate practical concerns outweigh long-term aspirational goals. That exploration is a luxury we can't afford. That the problems here are more urgent than the possibilities out there. That we're better off staying home. Neither choice is wrong. Both are defensible. But they lead to very different futures. The footprints left by the Apollo astronauts are still there, preserved in the lunar dust. No wind or rain to erode them. No geological processes to bury them. They'll last for millions of years, long after everyone alive today is gone. Long after our civilizations have risen and fallen, those footprints will remain. Evidence that humans once came here, once walked on another world, once achieved something extraordinary. The question is whether they'll be joined by new footprints, whether the next generation will add their marks to the lunar surface, or whether those 12 sets of footprints will stand alone, the only human traces on the moon. a monument to what we once did and then abandoned. The Apollo program was a singular moment in history. A convergence of political will, public support, technological capability, and national rivalry that made the impossible possible. It lasted less than a decade. 6 successful landings. 12 astronauts on the lunar surface. 382 kilograms of moon rocks brought back to Earth, or 842 pounds. Thousands of photographs. Decades of scientific data. And then it ended. Not because we'd learned everything there was to learn, not because we'd exhausted the possibilities, but because the political moment that enabled it passed. The Cold War space